Well, welcome back again, everyone. What we talked about last time was the motivation behind building a clinical prediction rule. And I gave you an example where some investigators had enrolled people who were admitted to a particular hospital, admitted to the intensive care unit of that hospital, collected risk factors on them, and from those risk factors developed a logistic regression model to predict a person's risk of dying in the hospital. That was the outcome they were trying to predict. Let's suppose you do that. Let's suppose you build a prediction rule for whatever outcome you're trying to predict. And now you want to judge whether this prediction rule is worth using, whether it's valid in some sense, and whether it's worth using on future people. So what I'd like to talk about now is how we go about evaluating the performance of a prediction rule to decide whether it's good or not so good to use on future people. Well, as a roadmap, the first thing we think we need is to have some numbers, some metrics, some measures of performance. How do we quantify in a number or two how well a prediction rule is working? And there are a number of ways of doing that. A number of statistics that will be routinely published whenever you fit a prediction rule with a data set using a software package like Stata. But typically there are two types of performance measures. One is called measures of calibration, and the others are called measures of discrimination. I want to talk about calibration first. And then later on, we also have to extend these performance measures and our estimation of their performance measures into deciding how we're going to measure them, on what people, what data sets are we going to use to measure calibration and measure discrimination. Because remember, what we want is a model that not only works well in the data from which it was developed, and that's almost always going to be a truth. It's because you're going to build a model that works well in this data set. What you really want to know is how well will the data work in another data set, in future people. You want to know its ability to calibrate and discriminate in future data sets. Well, how are we going to do that? Well, I'll talk about a few methods. I'll talk about the method of just resubstitution, which is usually not adequate enough to decide whether a model is going to work well, whether the measures of calibration and discrimination are adequate or not. I'll talk about maybe the more ideal situation where you have another independent data set that was not used at all when you built your prediction rule, but you're using it now to evaluate the prediction rule that was built on one data set to see how well it performs on another data set, an independent testing data set or validation data set. And then finally, I want to talk about a couple of other methods which are based on resampling techniques, things like cross-validation and bootstrapping, that can be used when you don't have an independent data set, when you only have the single data set from which you built your model, and you want to come up with an honest, valid estimation of how well that model might work in future people, but you don't have any other future people to test it in right now. Well, so the methods of assessment, we'll talk about that in future lectures, but first let's concentrate on this notion of calibration as a performance measure to describe how well your model is working. Well, first, what do I mean by calibration? Calibration refers to the agreement between what the model predicts, which is an estimated risk, and what the actual outcome is. So let's think about that for a minute. Let's suppose we go back to that mortality prediction model, the one that we had in the previous example. I took a person, 50-year-old person, blood pressure 120, ran that person's risk factor profile through the model, and ended up saying that person's risk is 6%. Now that estimated risk might be used by physicians in real life to decide what to do with this person, whether the person should be monitored closely or the person should be monitored less closely, because the prediction risk says his chances of dying in the hospital is relatively small. It's only 6% chance. Okay, so if we're going to build clinical practice based around that estimate, we have to be pretty darn sure that that estimate really reflects truth, that the estimated risk we're getting from the person, 0.06, really matches up with his true risk. Well, the problem is I don't know my true risk. If I get admitted to your intensive care unit and I survive my hospital stay, does that mean my risk of dying was 0? If I died during the hospital stay, does that mean my risk of dying was 100%? Well, probably not. Probably your risk is somewhere between 0 and 100%. And one person's actual outcome, either dead or alive, is not going to tell me what that person's risk is. people who have a risk of 90%, some of them are going to die. You'd expect 90% of them to die, but 10% not to die. So just because someone died or just because someone didn't die, that doesn't mean their risk was high or low. So how can I measure calibration? What I can measure, since I can't measure an individual, what I could do is I could measure it on a group of individuals. So what I'm going to do is I'm going to compare actual outcomes to estimated risks for subjects, for groups of people who have a common range of estimated risk. So what I'm trying to say is if I had 100 people, all of which had a predicted risk of 6%, what would be evidence that that 6% is valid, that it's calibrated? If 6 people die and 94 people don't die out of those 100 individuals, so the observed proportion of disease, cumulative incidence, is 6%. It matches perfectly with each individual's risk, which was 6%. So if I stratify people according to sub-ranges of risks, so in other words, I take 100 people, all with a risk, a predicted risk. I'll put a little hat over it to stand for predicted, of 0.06. What would I expect if this 6% predicted risk was accurate, if it was calibrated? What I would suspect are 6 deaths and 94 non-deaths. If so, I could say my estimated risk of 6% is well calibrated. What actually happened to these people matched up perfectly with what was expected to happen to people. So let me give you an example of how you can show that in practice. I'm going to go back to the mortality prediction model that we talked about in the previous slide. And what I've done here is taking a table from one of their publications of what happened to 1,997 people who were admitted to their hospital. And what the investigators have done is they've broken those roughly 2,000 people into 10 subgroups. 10 subgroups of predicted risks from the clinical prediction rule. There are 967 people out of the roughly 2,000 people whose predicted risks were between 0 up to but not including 10%. There were 49 other people whose predicted risks were between 90 and 100%. So we're stratifying people into subgroups of similar predicted risks. And what we want to see is if the actual expected number of deaths match up well with the predicted number of deaths. If so, I have good calibration. So among these 967 people, all of which have a predicted risk between 0 and up to but not including 10%, there ended up being 38 deaths observed from those people when they were hospitalized. Now, how many deaths would be expected to happen among those 967 people? What's the expected number of deaths? Well, the number turned out to be 41.9 deaths. But how they got that number is each of these 967 people have a predicted risk. What they did is they added up each person's predicted risk for all 967 people, and that ended up giving a total expected number of deaths of 41.9. So to judge the calibration of their predicted risks, you want to compare the observed number with the expected number for each of these 10 different subgroups of people. So for the first subgroup, they predicted there'd be around 42 deaths. There ended up being 38, a little bit less than predicted. In the second group, they predicted 52.2 deaths. There ended up being exactly 52 deaths. That seems to be right on target. The next group, they expected around a little bit more than 48. They got exactly 50. A little bit, but very close to target. The next group, they expected almost 49. They got 47. So row by row, you can look across this table and compare the observed to the expected number of deaths. And the message I think I'm getting is that these are pretty close to one another. This means there's good calibration. What actually was expected to happen to the group of people actually did happen to the group of people. Now you can take this a step further. You can combine these into one number or one test of significance to try to describe the calibration. But the table itself, I think, gives the reader the ability to look at the results themselves row by row and get the gut reaction that I have that this prediction rule is working pretty well. That what was predicted to happen to people with a common predicted risk as a set actually ended up happening. And that's what we mean by calibration. Well, the next time we get together, I want to look at the next type of performance measure, which is discrimination. So I'll see you then.